This is the lab on Ohm's law and resistors in series and parallel. And here's the motivation, as in all electronic circuits we are using resistors left and right everywhere. So knowing something about resistors is really important to the world we live in, because we just use it everywhere in any electronic circuit and any electric gadget. Right, so let's go ahead. Here's a little bit of the theory: series circuit, parallel circuit. Then this is, of course, the equipment, the snap circuit. And then the first ones that I have here are a bunch of experiments that I had designed for kids, like some like third graders, sixth graders, even younger kids could do these, maybe with fewer instructions. And I'd like you to do them too, respectively. Here I'm going to do them in the video, of course, for you. So this would be just to get familiar with the snap circuits. So at some point I decided to put these early on. And then we're going to actually get to the actual measurements. And these pages are important because it shows you how to measure voltage, which is measured by putting the leads on both sides of the component that would be measured. By the way, it's the same thing for measuring ohms, except for measuring ohms, there is no battery connected. Measuring volts, there is a battery connected, of course. Measuring current, that's different. You take out a piece here. You see this one here is missing, right? So you take it out, and that's where you put the leads, and this is where you're gonna measure the current. And then here is the resistance, and as I said, that's the same as the volts on both sides of the components, but notice on the top here the battery must be disconnected. All right, so here's the experimental procedure then. This is the color code for resistors. They're really small. You can see them. Actually, this is off the picture right now. You can see them really small here. Yeesh, right there. And so they have to be color coded because they're just too small to put numbers on them. So they have a certain color code and people can read them readily, except I usually need a magnifying glass, and so do students. So we're gonna do this one here next. Then you have to figure out with the color code, what do these colors actually mean, and they do mean the numbers 0 through 9, so that's what you have to fill in. By the way, this is a giveaway here. They're usually gold, and there are 5% tolerance. Silver would be 10% tolerance, but I don't have any of those. And then you have to figure out what these 3 bands mean, four bands, because the last band significant is the tolerance. So plus minus 5%, it's supposed to be 180 ohms, but it could be as small as 171 or as high as 189 ohms, because that's 5%. Okay, then this one here with number of light bulbs, we'll do that. And then we'll start with just one resistor in a circuit. By the way, I should have mentioned earlier, I mentioned it now, still early on, this is going to be a really long lab. And it usually is. We try to push people and in a lab intensive, and even there it is 2 hours long at least. All right, this is my example then for resistors in series. So, and some of the things to point out here is that when we have these different resistors in there, notice the blue ones here, we measure or compute them 5 different times, and each time we come up with virtually the same result. So that's what we're looking for when we're grading. So, and you notice that they're all relatively close to each other, either within 1% in fact, but I mean that could be attributed to the tolerance. It's also, of course, a measurement. This one here is the resistance according to the color code. The reason why I cross these out is because they're usually given there in the lab manual, but I might just use different resistors that day. And this here is the measured ones. Then here is the voltage, and in the series circuit, the voltage on each one adds up. Notice also that the higher the resistance in a series circuit, the more voltage it takes. The current is the same everywhere. So these things, current the same everywhere, voltages add up, and the total resistance here simply adding up are hallmarks of a series circuit. And then over here, again, they're computed and compared over here with Ohm's law, they're computed, and then compute the power as well. Sometimes people actually forget to fill in the top row here, but this has to be measured, and of course I will do it. So please fill it in as well. Okay, so here's the data table then for resistors in series. Yeah, and everything that's in blue here would have to be measured or calculated. I will in the videos actually measure these here, and you would have to watch the video and write down those numbers. I'm not going to put them all in. And then you also have to compute everything else that needs to be computed. And I didn't mean to do that. Okay, ignore this little table over here. Let's see, same thing here. These are in parallel, resistors in parallel. And, well, you'll see what happens then. And again, I'm not going to have the same ones. I'm going to use different ones because whatever I have in the bag today. And that's actually it. Still, that will take a long time. There will be no conclusion, as I have for the rest of the semester. There is an addendum here, but you're not going to do that. All right, let's get started with these 10 experiments, which I will do within 12.5 minutes. And then we're going to continue with the color code, and then these lamps here, and then resistors in series and resistors in parallel. All right, I got 10 projects here, which students would normally do to get an introduction to the snap circuit. So I'll build the first one here: battery, 1 lamp switch, some wires. So switch, turn it off, lamp, and some wires, and then turn the lamp on in a moment. Oh, there it is. That's the one I wanted. Okay, and yes, the lamp glows. Let's see, is it bright? You would have to answer that. Take out 1 wire. Why doesn't the lamp glow? Even after the switch is on. There we go. Insert the wire, but take out the battery. Why doesn't the lamp glow? So these kinds of things, and you would have to answer these. Of course, these are adapted from kids, but I figured they are also a good introduction for adults. So let's see. Next one, let's see if I can do these 10 projects actually in less than 10 minutes. That's going to be a challenge. The electric circuit, battery, lamp, exactly 1 wire. Here it is: paper, pencil, crayon, paper clip. So, okay, that doesn't connect. Let's see, that pen here apparently is not metal enough. How about the paper clip? Let's see. And yes, it does. And the highlighter, nope. All right. Build an electric circuit that contains battery, 3 lamps in series, switch, some wires. All right, so 3 lamps in series. Series means one after another. So actually, I can build like this because there's one after another. And did it say switch? Oh, it did say switch. Yes. All right. Of course, I have a few extra parts here simply because I took 2 of these bags with me. Alright, and there we go, and whoa, barely, and it doesn't really matter. I have plenty of other lamps over here, but in series they don't glow very bright. Okay, build an electric circuit that contains battery, 3 lamps in parallel, switch, some wires. Alright, so this time I'm going to put them in parallel. Notice that they were in series a moment ago. Now they're going to be in parallel, and I have to remember that I have to have the switch in here. So actually I can do it here, 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 and I can do it even easier. Hold on. There and there. So that's actually easier to connect. There's a reason why this won't work later on when I have to measure resistors, but for now this works just fine. I just cannot put it on top. The reason why I can't put it on top, if you might see this here in the camera, that at the bottom it looks like it connects, but it's really not tapping on top there. If you put it like this, it's just not clicking there. So I put the lamps on top. Again, for resistors later I have to do different solution. Okay, turn it on, and yes, they're pretty bright. So how bright are our lamps now, and so on. Built an electric circuit that contains battery, LED lamp, resistor, yellow, switch, some wires, and so on. So I'm going to do that. This one here is the LED, and I'm going to put it here. It did say switch, yes, there we go. And some wires. Oh, it did say the resistor. All right. And here we go. And let's see, it doesn't do anything. So what about if I turn the LED around? Light emitting diode. And there it is. So apparently it has a certain polarity, and there's a reason for this arrow on here. Okay, built this electric circuit with LED instead of loudspeakers. So the camera is sideways, so I'm building the sideways as well. I have to take the U2 here. Let's see, where does this one go? Somewhere there, and the LED does have to be connected like this to there. And let's see, LED and so loudspeaker, so I have that, and any kind of switch, doesn't look like it, and then any kinds of connections here. Oh, well, that's going to be interesting. So, okay, it's not exactly like that, but it'll be okay. I got plenty of these. And something over here. And I think I got it. And apparently it blinks. Okay, I'm gonna stop the video now here so it doesn't get too long. I'm gonna do the other 4 in the next video recording. Alright, I just noticed that the other 4 projects need a little bit of time to build, so I don't think I'm gonna make it in less than 10 minutes that I promised earlier, so let's see. Alright, and then it says, do not remove any parts, use a jumper wire to turn off the annoying sound. So let's see if I can do that. So I have to click this somewhere here, and okay, that, oh, there we go. Why did that work? Well, why did it work? Because where's the current going now? Can you see that here? Actually, this way. So why does it work? Why does something else may not? Well, actually that works too, kind of, yeah. Not too bad. It's at least quieter. Yeah, so if I do something like this here, it's not working very well. Alright. So here it is again. There, turn it off. There we go. Alright, built this electric circuit, built the next one. Learning how to build. After the music has stopped, clap your hands and so on. Alright, so I'm going to rip this apart here. I'm going to use the Space War. No, don't use that. Use the music IC. There we go. Put that here, I believe. And a long one over here. Think so. Switch in the off position. A whistle chip over here. Gosh, I keep looking at the wrong one. There's so many drawings on my page. I kind of lose track here. I need this one and 2 jumper wires. I'm going to connect them apparently over here and here. And now I'm almost done. Just have to do this one here. And turn the switch on, and if I didn't make a mistake, there we go. Alright, and now it says clap or whistle. Okay. Okay, there you go. Alright, and build the next one. By the way, if you read up on the whistle chip, it'll tell you that it works on pressure. So as you exert pressure, there's a little metal piece in there that all of a sudden makes a connection due to the pressure increase, and then there you go. Alright, so space war thing in the meantime. Right here, that's how it looks like, and I have an RP photoresistor over here that kind of goes here, and the speaker over here, and then the rest are gonna be wires all over the place. And here we go. Of course, as you see, this would be a lot of fun if you were able to do that, so I'm sorry that I just can show you that in the video. I have to get up and check if I'm actually filming the correct parts here, not to make a mistake. And there we go. Oh, cover the RP photoresistor with your flat hand. Okay, actually, oh, okay, so it changes kind of the circuit inside. Alright, and I believe it's the last one, so build this electric circuit with a different layout, and there's a lamp and there's a switch in there. Whoa, this looks complicated, this last one. I thought this was just the motor, but it's not, and then there's a switch. There we go. Still have to check sometimes if this one is actually on. Lamp and another switch, okay. And let's see, lamp and another switch, and they're supposed to be in parallel with each other, and then connected to this one over here, and then all the way back apparently. Alright. Very end it became a little complicated. Alright, here we go. Oh yeah, I can put that one on there. Let's see, actually, I have to turn this around to begin with. Plus on plus. And then, let's see, turn this one on, and it turns nicely. When I push the switch here, then the lamp actually goes out. The lamp is actually relatively faint because it's in series with the motor. The motor is also getting slower when the lamp is on, but here when the lamp is off, because the switch and lamp are in parallel, so I have a little short over here, then of course it's only the motor. And I turn it off, and then it says what happens when you push the press switch. Turn the motor around. Okay, I'll turn around. Ooh, this following thing might not work. And that's possibly because I have a lamp in there, and the batteries might not be strong enough. And then turn this one off. Yeah, it doesn't lift. It's supposed to actually lift, but the batteries aren't strong enough. Error tries. Okay, did I make it within 10 minutes? Nope, I didn't. 15 almost. Alright, this is the color code for resistances, and this may or may not work here with the magnifying glass. So this one here, they all end in gold, and for most of them, with one exception, the second to the last band is brown. So I'm just going to read off the first two. So this one here is brown, black, and then brown, brown, gray, and then brown. This one here is red, and I have to look at it at the same time. This is red and yellow and then brown. And then I'm going to go back here because I keep looking through the magnifying glass. I should look through the viewfinder. Push these up a little bit. And so the fourth one that I have here, I believe, is red, violet, and then brown. And then this one here is green. Let's see, can I see that in the viewfinder here? Green, blue, brown, and then I have a couple more over here. So this one is violet, green, brown, and then the last one is triple orange, 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 orange. Okay, I'm gonna measure them. So this one here is from the kit, actually. That's why it's already mounted. So this one is 102 ohms, and of course it does say 100 ohms on there. So I jot these, I'm just gonna jot these down for myself, but I let you actually watch the video and write them down. So this one here, these are a little nicer. I can nicely put these in, and then it still wiggles a little bit. By the way, my ohm meter is on 2000 ohms, so that's the largest I can possibly measure at this point. So this one says 178. Then this one here, so going down the list, is 238. This one is 269. So I will let you jot these down from the video, but I'm actually supplying what the resistance should be. 550, how much is it? 500 and, seriously, let's call it 560, which by the way is what it is. Okay, I'm going to take these two out and the last two in here. So this one here, 751. Okay, and for the last one, I actually have to turn the ohm meter to 200 kilo ohms, and I'm measuring this one as 33 kilo ohms or 33,000 ohms. By the way, I could have also measured all of these here by clamping them in my fingers like that, and then and then dial back, I guess. There we go. So it would have worked too. All right. And then you would have to figure out what are the colors associated with. Okay, so this is assembling light bulbs in circuits. Going to start out with one light bulb. So, and there we go. And it's relatively bright. I'm going to measure the current. This is the only time that I have the ammeter on 10 amps for the lamps. Otherwise, it's always going to be one lead down here, one prong down. Right, I have to disconnect here, and this is where I'm going to put the ammeter in, and then I'm going to read off apparently 0.22 amps. Forget about the negative, because this is all I need to do. This is how I get rid of the negative. Still 0.22 amps. Okay, so anyway, that was one light bulb. Okay, now, and then of course you would have to calculate how long that light bulb will glow, provided that two regular AA cells give you a total of 3 amp hours. I take that back. One regular AA cell, 3 amp hours, while there are 6 amp hours for 2 of them. And so basically you just have to divide 6 amp hours divided by 0.22 comes out to roughly 30 hours almost. 6 divided by 0.22, top of my head. Alright, So 3 lamps in series. And there we go, and it's easy to see that they're very faint in series. The reason being is that they have to share the voltage that comes from the battery, and on top of it, because their resistance adds up according to Ohm's law, they also drive the current down. So that's why they get like a double whammy: less voltage each, less current each. The amount of amps that go through here is 0.12 amps, and so again you would have to see for how long they would last. They would actually last longer because they're so faint, they don't use that much power. Alright, then I'm going to do 3 light bulbs in parallel, and if you're guessing that as they're in parallel they're just going to be as bright as the one light bulb, I mean each of them as bright as the one light bulb, then you're right, they are as bright as one light bulb. But of course there are 3 of them. I should expect that the current that I get here is 3 times as much, and it is 0.60. And of course you would have to figure out that, well, when you compute the time that the batteries would last with that, well, it's 6 amp hours divided by 0.6, so that only comes out to 10 hours. Alright, and then I have this extra circuit here on the right hand side that I already filled in, but might as well build it. So I have 2 of them in series, that, and one of them in parallel with these. Let's see. Whoops. I want to do that. And for this one, I'm just going to use this jumper wire. There we go. And we can see that the 2, of course, in series are much fainter than the one that's in parallel, because this one gets the full voltage, these 2 have to share the voltage, and then the current that goes through this one is larger than the current that goes through this one. Overall, if I just measure the total current, and I can do that right here, unplug that and measure it right here, I do come up with 0.36, let's call it 0.36 amps that they all draw together. And that's it for this part. So this is the circuit with 1 resistor. So I'm going to leave the switch out, because I noticed in the past that sometimes the switch actually would take up some voltage. And so I'm just going to do it without. Okay, closed circuit, so there's a current flowing. Of course, there's nothing really to see. It's just a resistor here that uses up the energy, and I see it in this case. Does it in an electronic circuit too, but then there's a point. It's supposed to limit the current in an electronic circuit, and again, there are tons of them, millions of them in modern circuits. All right, I'm going to measure the resistance first. Of course, I already did that earlier. This is the brown, black, brown one. Oops. Yeah, brown, black, brown, which means it should be 100 ohms. And when I said oops, no, I meant to take that off, because I need to measure the resistance without the battery. So the battery is not connected. I just hold it up here. So 101 ohms, but I had measured that earlier. Then I'm going to measure the voltage. So I'm going to switch this one here to volts. And there we go. And that is 3.14 volts. That's pi, which makes sense because that's the voltage from the battery, because it's the only thing in the circuit. And finally, I'm going to measure the amps. I put it back on this one here so I can measure milliamps. I'm guessing I'm going to measure in that region here. So I took this one out, and where I took it out, that's where I'm going to put the ammeter in, and sure enough, I'm measuring 30.3 milliamps. And then it's up to you to compute the resistance with Ohm's law and the power with the power law. Okay, this is the circuit with the 4 resistors in series. I had, I believe, 7 resistors. I definitely took out the 33,000. It would work, but it's just going to throw off the results that in such a way that we really can't figure out parallel and series circuits. So they have to be different, but still relatively close to each other. So among the remaining ones, I chose the 180. And let's see if this actually shows here in the video. 180, the 270, the 560, and the 750. That I put them in order shouldn't matter. However, if I do put them in order, then actually we will be able to see a pattern. Okay, when I built this one here, I pay close attention to my circuit drawings the way it should be. So I have to make sure that they're really in series with each other. So here we go. How I then arrange them in series this way or that way, as long as they're in series with each other, that'll work. So I hope I still have them in order. And once the circuit is complete, I have a closed circuit and there's a current running here. Alright, I'm going to unhook the battery here so I can measure the resistances and double check that I really do have them in the correct order. So this one here says, oh, where am I? Oh, I have to go down to 2,000 ohms to measure. Okay, that's the 180 ohms, but since it's a measurement, do write down 178 ohms for the measured resistance, because apparently this one is, it's just a little bit lower than what it should be. Then the next one here comes out to, trying to jump all over the place here. Ooh, I don't know if I want to use this one. Wonder what happened. I don't know. 266 ohms. Next one. Nah, what's going on here? 551 ohms. Of course, we measured these earlier, but it's good to measure them again. And then I can see that I do have them in the order I want. 750 ohms. There you go. All right. Back to a closed circuit. Oh, no, not back to a closed circuit, because I just forgot to measure the total resistance. So total resistance is all the way through here. So from the very first to the very last, with the battery disconnected. And let's see if I'm actually exceeding 2,000. I don't think I do. So 1,747 is the total measured resistance. All right. And you will see that, yeah, the resistances add up to the total in a series circuit. All right. Reconnect the battery and put this on 20 volts. So now I can measure the voltages on each. And you should be able to see a pattern. And again, let's see. Let me get rid of that negative there. There we go. 0.31 volts on the smallest resistor. 0.48 volts on the next resistor. 0.99 volts on the next resistor. So you can see the pattern there. Apparently, the larger the resistance in a series circuit, the more voltage it gets, and 1.35 volts, and then you would have to add them up, and you will see that that is indeed the total voltage which I'm measuring right now. So total voltage is 3.17 volts. I know earlier it was 3.14, but I guess it's a measurement, so which of course is the battery voltage. There it is, 3.17 volts. All right. Then, measuring the amps. So wherever I measure the amps, this is where I'm going to take something out. I'm going to put this down here to the milliamp region here. So I'm going to measure right here between these 2 points, and I'm measuring apparently, again, forget about the negative, 1.6, no, what is it? What is it? Come on. 1.79 milliamps. That would be the first resistor. The second resistor, 1.80 milliamps. Virtually the same, right? Then the third resistor, 1.80 milliamps. The exact same. And the same as the first, within tolerance, But that makes sense that in a series circuit, the amps going through each should be the same. By the way, it's a little bit easier if I just do this one here when I unhook them, because then I can just rest them in there. 1.80 milliamps. And finally, the total current, but they're all the same anyway, so the total current also should read the same thing. 1.80 milliamps. And I think I got it all what I needed to measure, and the rest is computations. So this is the 4 resistors in parallel, and here I'm paying close attention to my circuit schematic, because if I just do it too tight, obviously they're in parallel now, if I do it too tight, then would be really hard to measure the current, and so that's what I'm doing. It looks a little bit more complicated than what it could be, but again, I do have a reason for that. So here's my parallel circuit here, and then they're connected all on this side and they're connected all on this side. I know I could have just taken one here, put it underneath actually, but it just would work very badly for measuring the amps. So in any case, let's go ahead. First I'm going to measure the resistance, and of course I have to unhook the battery. So I'm going to measure the resistance of the first resistor, and I get 80 ohms. That's actually interesting. It's not supposed to be 80 ohms, right? It's just that resistance that I had earlier. Turns out, of course, I'm actually measuring everything because they're all connected with each other. Yes, they're disconnected from the battery, but they're connected with each other, which means that if I want to measure each individual resistance, well, I have to disconnect them from each other. I knew that. And of course, here I ought to get the same as before. Oh, I mixed them up. Did I mix them up? 270, 180. So this should be my first one, actually. That's a 550, and again, you can just, that's a 750. So you can jot that down from earlier, and it turns out I have to take it all apart, because I don't have to have them in order. It's just that it's just easier to see a pattern. So now they're in the same order as I had them before, top of the list. And there you go. So this is, I believe, the 180, and then is it the 200 and something, right? And then 560, and then 750, I believe. All right. So now that was actually the individual resistances. Now comes the total resistance. So I connect them all. And unlike in series, where they simply add up, that's not the case for parallel circuits, where, of course, as you saw in the theory part, they add up as reciprocals, and that's what you have to figure out. You have to add them as such. And so the total resistance is actually that 80 or 81 ohms, let's call it 80 ohms, that I had earlier. And it doesn't matter where I measure that, it's always going to be those 80 ohms with intolerance. I could even measure like this here, any which way. I always get the 80, 81 ohms, I guess. I don't know why it's doing that. Hey, stop jumping all over the place here. There you go, there you go. All right, so 80 ohms is the total resistance. Okay, then I'm going to connect the battery. So now I have a current going, and turn on the voltmeter, and now I'm going to measure the volts on each of these. And again, get rid of the negative. All right, 3.12 volts on the first one, 3.12 on the next one, 3.12, and that makes sense because they're all connected on this side with each other, on this side with each other, so I ought to measure the same voltage across each of these here, which again, or which also is a hallmark of a parallel circuit. The total voltage, by the way, same thing, 3.12 or 3.13 within tolerance, you know. Okay. Now comes that was the total voltage. Now comes the amps. I'm going to put it, let's see if I should be able to get away with that milliamps. Okay, here's the total current that I'm measuring. Okay, that's actually, whoa, okay, I have to get one higher there. It's more than 20. Nah, come on. There we go. Forget about the negative. So 38.1 milliamps. And by the way, if you divide 3.14 volts by 38.1 milliamps, and then shift the decimal point because you divide it by milli, so multiply by 1,000, you will come up with something really close to 80 ohms. Ohm's law. Voltage divided by current is the resistance. Okay, so that was the total current. Now the current for the first resistor. That one is 17.3 milliamps, and yes, let's get rid of the negative here. This one is easy, just put it in there. 17.3 milliamps. The next one, this is why I build it that way. 11.5 milliamps, so that it goes up in resistance here, but apparently it goes down in current, which is that saying that you have heard before, path of least resistance. That's true in electricity. 5.5 milliamps, and then for the largest resistor, I got 4.0 milliamps, and these are all the measurements that you need.